Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencastr. Zencastr is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencastr has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencastr paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your
Grand Canyon University, an affordable private Christian university, is one of the largest and fastest growing universities in the country, offering more than 270 programs online. In addition to federal grants and aid, GCU's online students received nearly $130 million in institutional scholarships in 2022. Find your purpose at Grand Canyon University. Private, Christian, affordable. Visit gcu.edu/myoffer to see the scholarships you may qualify for.
I'm Sofía.
And I'm Gabriel.
And you're listening to a Breaking Math Problem episode about the irrationality of the square root of 2.
There are many proofs about the irrationality of the square root of 2, some that are published even as recently as the 1950s. You can read more about that on the Wikipedia page. I found that very fascinating in the research for this episode.
Yeah, and so before we get started, we're going to do a couple of plugs. If you want to get a poster, we have a beautiful poster out, so get that on facebook.com/breakingmathpodcast for $19.65, and that includes shipping and handling. We also have Patreon. If you donate $1 a month to us, that's 3 cents a day, you could get ad-free episodes, and we load them up there earlier by either a few minutes or a couple days, whatever, than the stream, so you could get those there. We're on Twitter at BreakingMathPod if you want updates about the show, and we have our website, breakingmathpodcast.app. And if you want to email us ideas, comments, questions, or corrections, you can do that at breakingmathpodcast@gmail.com.
We also have a sister podcast that is available on YouTube and also wherever podcasts are played, and that is found at youtube.com/Touring Rabbit Holes Podcast. You can also search for the Touring Rabbit Holes Podcast on any podcast player as well. And that's done with myself as well as Dr. Alex Alanis, whose specialty is particle physics. Very good show.
Oh, yeah, absolutely. So, yeah, I mean, so this goes back all the way to Archimedes and the legend of Hippasus of Metapontum, who divulged that the square root of 2 was irrational, and according to legend, they murdered him for it. And so this was a pretty big deal to them because they thought that everything should be representable as the ratio between two whole numbers.
Yeah, it's fascinating that some knowledge can be forbidden and that somebody could actually be murdered for it, but history is filled with that kind of thing.
Oh, yeah, absolutely.
And real quick, I know that you had mentioned that Archimedes kept this a secret. Rather, he kept it a secret that the square root of 2 is irrational. I'm wondering, is there evidence of that, or is it assumed based on what we do know about him that he probably was aware of that fact?
I can't remember actually where that part of the construction comes from. I think eventually it was accepted by the Archimedeans. I think that's something about that. But honestly, I haven't seen the original historical records or anything about this. So okay. I'm not totally sure.
Interesting.
Yeah, so if the square root of 2 is irrational, that means that its decimal representation, for example, never repeats itself. Because 1/7, right, it's like 0.146 6 something, like has 6 digits that repeat over and over again.
Yes.
And 1 divided by 9 or like 15 divided by 99 is like 0.1111 or 0.151515, right?
Mm-hmm. Yeah, so that one actually repeats, but a non-repeating decimal number is what we're talking about here.
Yeah, and which means that you could write it down until you have 30 hard drives full of digits. Eventually you'd run into a sequence that isn't anywhere on those hard drives if you just keep going.
Yeah. Now, there's irrationals that are pretty popular, including things like pi. One thing that was interesting in the research for this episode is that pi is what was the term?
Transcendental number.
It's the transcendental, but also it's a universe creator, something of that.
Oh yeah, it's some people have called it a universe factory. There's an XKCD that I like where it says like pi equals 3.1415926, and then it says, help, I'm trapped in a universe factory, mine 59. Because the thing is about pi is because since it's transcendental, it has every decimal representation contained within it, meaning that in any way that you can write the universe down as a set of numbers is contained somewhere within pi.
That is wild. That is absolutely wild.
Including a universe where everybody is the same except for they have British accents.
Wow. That's the crazy thing about mathematics is the universality of it. Wow.
Oh yeah, and just you run into these bizarre things. But square root of 2 is an algebraic number, meaning that it could be made with compasses and a straight edge, and therefore it is not transcendental.
Yes,
it is. Because the algebraic numbers can actually be enumerated, so you can have all the algebraic numbers in a row.
Yes, and as we said earlier, so this is a problems episode where we will be proving that the square root of 2 is irrational, and this is again there's many different kinds of proofs here, and we're doing an interesting one. I kind of like it. It involves evens and odds.
Yeah, and the proof structure is this. It's an infinite descent proof, which is a type of proof by contradiction. So, Gabriel, we've done proof by contradictions in the past, right? Do you want to say kind of what that is?
Yes. A proof by contradiction is when you start off with an assumption, with a truth claim about something, and then you go through the proof and you show that the proof couldn't be correct, or rather, the conclusion of the proof is something we know to be incorrect. Therefore, the original assumption is incorrect.
Yeah, and not only is it incorrect, it's perfectly incorrect. Meaning like in such a way that you have to assume it's opposite. So if me assuming, for example, that the listeners of this show are fish leads me to making a series of business decisions that are blunderous, like only promoting fish food on the show, things like that, then we have to make the assumption that my initial assumption was wrong. That was a little bit of a stretch, but
well, again, even not necessarily. Cause, I mean, not to get nitpicky here, but I see what you're trying to say about proof by a contradiction.
But so we're gonna assume to start with what we think is false, and what we're gonna show is false. And that is that the square root of 2 is equal to p over q for some integers p and q. And so this might be a good time to talk about what infinite descent is. Infinite descent is a type of proof by contradiction where you assume that something is already in its most basic form, and you show that no matter what form it's in, there's a more basic form. And that means that you could just keep going on forever. And with integers, you can't go on forever, right?
Yes.
If you keep just decreasing with integers, you're going to reach a point where you stop.
Yes, yeah, exactly. And as you said earlier, we're starting off with the assumption that the square root of 2 can be shown or can be represented by 2 single integers, p and q.
And they are relatively prime, right?
Yes. And this is the definition of a rational number. So, we know this is incorrect, but we're just going to say it's true for this proof.
Yeah, rational doesn't mean that these numbers, like having talks about sound environmental policy or anything. It means that they're based on ratios, rational.
Yes, yeah, exactly. Ratios. And again, as you said, infinite descent, that does sound almost fractal in a sense.
Oh yeah, and basically, an infinite descent doesn't work if you have fractions and stuff that we're working with. But since we're working with integers, infinite descent works. It would also work with ordinals, for example, if you want to go back and listen to the ordinals episode.
And we're just going to use a little bit of algebra in this proof, and we'll be done before you know it.
So if the square root of 2 equals p over q, what happens if we square both sides?
In algebra, what you do to one side, you do to the other. So if you square the square root of 2, you get 2. And if you square the other side, which is p over q, you get p squared over q squared. So 2 equals p squared over q squared.
And if you multiply both sides now by q squared to make sure we don't have q squared on the bottom, you get 2q squared equals p squared.
Brings me back to early middle school algebra, getting rid of that denominator. 2q squared equals p squared.
Now, what does that say about p squared?
It means that p squared is even because it can be divided by 2.
Now, p squared is even probably means that p is even, right?
That is correct.
But we want to prove this because we're being, as careful as we can. Because, for example, for all we know, q can be 1 and the square root of 2 can be some other integer based on what we have so far.
Yes.
I mean, we could actually probably get rid of that possibility by saying p equals, by showing that 1 is not the square root of 2. But let's say we don't.
Yeah.
Let's just go the route of, so if an integer is odd, we're going to show that if an integer is odd, then its square is also odd.
Yes. You can think of any example in your head right now, but let's firmly prove it. The examples in your head, maybe say 9. We know that 9 is odd.
Yeah, and so 81 is also odd.
Yes. And also, the square root of 9 is 3, which is also odd. You can't think of an odd number that has a square root in which the square root is even.
Yeah, and what we're going to prove here is that specifically that if an integer is odd, then its square is odd. Because what we're going to do is we're going to look at kind of the opposite of that with evens. But first, let's go through this.
Sure.
So if an integer is odd, we could write it as 2 times some other integer plus 1, right?
Correct. Yes.
So, for example, 7 is 2 times 3 plus 1. 123 is 2 times 61 plus 1.
Yes.
So we're going to say m equals 2n plus 1.
Okay.
So what would m squared be?
Then m squared would be, you'd have to square the other half of the equation. So then you'd have to square 2n plus 1. Quantity 2n plus 1 times quantity 2n plus 1. We know the FOIL method from algebra, and you'd get 4n squared plus 4n plus 1.
And 4 is even, right?
Yes.
And an even number times times an odd integer is an even number, right?
Yeah, an even number times an odd number is always even. Is that what you're
And
saying?
an even number times an even number is even too, right?
That is correct.
So that means that 4n squared plus 4n is even,
Yes.
meaning that 4n squared plus 4n plus 1, which is m squared, is odd.
Yes, correct.
So now we're going to talk about the contrapositive of something, because we're going to take the contrapositive of what we just proved, which is that if an integer is odd, its square is odd. Mm-hmm. So the contrapositive of I am a human, therefore I exist in the physical world, and the contrapositive of that would be I am an incorporeal being, therefore I'm not a human.
Okay, there you go.
So if we have our statement, an integer odd means its square is odd, what's the contrapositive of that statement?
Its contrapositive is that a square being even means that its square root is even.
Yeah, and so we show that p squared is even, right? Which means that via this lemma, so since p is even, we're going to say that p equals 2k, right?
Yes, exactly.
So what would p squared be?
Then p squared would just be 4k squared for some value k.
And we already said before that 2q squared is equal to p squared. And recall that p over q was what we said the square root of 2 was.
Yes.
And we ended up proving that means that 2q squared equals p squared, which is how we got to p squared being even. And it's good to point out here that that p squared and q squared cannot both be even, right?
Correct.
Because if they were, then p over q would not be at its most basic form. It would mean that we could reduce it further.
Yes, yeah, exactly.
And since we can reduce it further, you have to keep reducing past 1.
Yes.
And since there's no integers less than 1, that's a contradiction, and that's how infinite descent works. So now we have 2q squared equals 4k squared, right?
Yes.
And that we could divide both sides by 2, and then we get q squared equals 2k squared, which says what about q?
It means that q must be even. But earlier, we said it must be odd.
Yeah, and we've shown by any number, we've shown within a proof by contradiction within this, and also just via infinite descent, that there's no p integers p and q such that the square root of 2 is equal to p over q.
Okay, excellent. Yeah, there we go. So there's a proof by contradiction using infinite descent. These are some really cool buzzwords for you.
I've noticed that all the proofs that I've seen for the square root of 2's irrationality, perhaps by necessity, because you're saying kind of what you can't do,
yes,
that it's irrational, are based on proof by contradiction and infinite descent. Another one that I like that I'll just talk about super quick is you take two squares, one that has twice the area of another, because so then the ratio of the two sides of the squares would be the square root of 2, right?
Yes, correct.
And we say that if they're integers, basically what you do is you prove that if they overlap, kind of like two napkins overlapping via the corner, that the overlap area would have to be twice would have to equal the area of the two corner squares. And then you basically prove that this could be done infinitely, and then you get another proof by infinite descent. But yeah, I just thought there'd be a good proof to show y'all, because it's something that we hear more or less kind of often in the math world, that, you know, certain things are irrational. But I think it's good to show what it takes to prove that something is irrational. And a good thing to maybe prove at home for you too is that if the integer, if the square root of something that is an integer is not an integer, then it must be irrational. And that might be something to prove at home.
Are we now going to, give our audience homework? Why not?
Yes. And first one to solve this correctly will get a poster if they're within the United States, or the file of the poster if they're worldwide. And so just send your proof to breakingmathpodcast@gmail.com, and we'll read your proof on the show.
Also, I'd love it if anyone were to send us your favorite proofs. Perhaps we'll talk about those on a future episode.
So yeah, thank you for listening to Breaking Math, and breakingmathpodcast@gmail.com, or breakingmathpodcast.app is our website, and you can buy our poster at facebook.com/Breaking Math Podcast. Just click on shop.
Until next time.